Hello and welcome to the Chemistry Solution. This tutorial is on conversions using balanced equations. A balanced chemical equation gives us the quantitative relationship between the molecules involved in the chemical reaction. So for example, this reaction tells us that 2 molecules of dinitrogen pentoxide decompose to give 4 molecules of nitrogen dioxide and 1 molecule of atmospheric oxygen. This equation could also be read that 2 moles of dinitrogen pentoxide decompose to give 4 moles of nitrogen dioxide and 1 mole of atmospheric oxygen. And we can use this relationship to tell us how much reactant would be required to give a certain amount of product, or how much product would be produced from a certain amount of reactant. It's important to remember, however, that these coefficients are equal to moles or molecules, but they are not equivalent to grams. And we use the coefficients in a balanced equation to convert from one reactant or product to another using stoichiometric conversion factors. For example, this tells us that for every 2 moles of N2O5 decomposed, 4 moles of NO2 are produced. We could also use this equation to tell us that for every 4 moles of NO2 produced, 1 mole of O2 would also be produced. And likewise, this balanced equation also tells us that for every 1 mole of O2 produced, 2 moles of N2O5 are required. Just like all the conversion factors we've worked with so far, these can also be written as the reciprocal. And really, you can make any conversion factor based on the coefficients from a balanced equation, as long as you remember that the coefficients stand for molecules, atoms, or moles, and not grams. So let's look at an example. How many moles of O2 are required to combust 3 moles of methane, CH4? The first step when doing any problem requiring a chemical equation is to make sure that you have a balanced reaction. In this case, we know that combustion reactions require O2 and that the products are always CO2 and H2O. And looking at the reaction given, we determine that it's already balanced. Now we will use dimensional analysis to convert from moles of methane to moles of O2. So we'll start with what we're given, 3 moles of methane, or CH4. Then we know we need a conversion factor to convert from moles of methane to moles of oxygen. And using the coefficients in our balanced equation, we can see that 1 mole of methane requires 2 moles of O2. And we'll put moles of methane on the bottom, so moles of methane will cancel out, leaving us with moles of oxygen. Remember that the mole ratio in our conversion factor is derived from the coefficients in our balanced chemical equation. Therefore, we come up with the answer that 6 moles of O2 are required to combust 3 moles of methane. But what happens if we want to go to or from grams? We know that the coefficients in a balanced chemical equation relate moles of one product or reactant to moles of another product or reactant, and that the moles are related by their stoichiometric coefficients. We also know that we can go from grams of a certain reactant or product to moles of that same reactant or product using the formula weight. So this creates a pathway of converting grams of one reactant or product to moles of that same reactant or product using the formula weight, then using the stoichiometric coefficients in our balanced chemical equation to go from moles of one reactant or product to moles of a different reactant or product, and then using the formula weight of that new reactant or product to go from moles back to grams. So let's try an example. What is the mass of iron produced if 8.75 grams of Fe2O3 is reacted completely according to the following equation? Again, our first step is always to double check to make sure that your reaction is balanced, and in this case it is. Then we'll start with 8.75 grams of Fe2O3. We know that we need to use a conversion factor. So what are we going to convert grams to, and how are we going to do that? Well, we know that we need to go from grams of Fe2O3 to moles of Fe2O3, and we'll do that using the formula weight. Make sure you put grams of Fe2O3 on the bottom so that it will cancel with the grams of Fe2O3 on top. Now that we have moles of Fe2O3, we can convert from moles of iron oxide to moles of iron. We'll do that using another conversion factor. And remember that to go from moles of one thing to moles of another, we need to use the stoichiometric coefficients in the balanced equation. Our balanced equation tells us that for every 1 mole of iron oxide, 2 moles of iron will be produced. And we found that mole ratio looking at the coefficients in our balanced equation. And we put moles of iron oxide on the bottom so it will cancel with the moles of iron oxide on the top. Now that we have moles of iron, we can convert to grams of iron, again using a conversion factor, and again using the formula weight of iron, or in this case, the atomic weight of iron, because it's an element and not a compound. We'll put moles of iron on the bottom and the atomic weight of iron on top. This allows us to cancel out the moles of iron. And then when you enter in all the numbers into your calculator, you'll come up with a final answer of 6.11 grams of iron. This tells us that if 8.75 grams of iron oxide is reacted completely according to the equation below, that 6.11 grams of elemental iron will be produced. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.